How do you know you have an polar bond, non-polar ionic? All you have to do is look up the electronegativities, subtract them, small from large, and then compare to this range. And if you get between 0 to 0.4, then that would be nonpolar. If you get between 0.5 and 2, that would be polar. And anything above 2 would be ionic. These are not, these scales are not set in stone. Sometimes people say, well, ionic and polar might be, ionic might be 1.8, etc. True, but some books, what I'm going to do is just going to stick to one of them, and that would be enough. So we're just going to use this. But again, you might see it slightly differently in other books or other resources. But actually, even that is still needs to get to the idea of what we call ionic character. So let's continue. So how do I know? So if I have something like H and an H, you know that's going to be a nonpolar bond. Why? Go look up the electronegativities. You get a 2.1 and a 2.1. So have it handy on you, please. 2.1 and delta En is 2.1 minus 2.1, which is 0. Where does 0 fall? Right here, between 0 and 0.4. So that's nonpolar. Okay. CH as well is nonpolar. So if you go look up the electronegativity of C, it's 2.5, and H is 2.1. (2.5) minus 2.1, that's a 0.4. Still nonpolar. Okay. OH. Well, let's look up the electronegativities of O and H. Well, we have H is 2.1, but O is 3.5. 3.5. Delta means the difference. 3.5 for O, 2.1 for H. That's a 1.4. Okay, let's see where that falls. Well, that falls between 0.5 and 2. So that must be what? Polar. So OH is a polar bond. And something like LiO, you go find the electronegativities. Remember, you take larger minus smaller. So Li is 1. O is 3.5. So you take 3.5 minus 1 for Li, and that's a 2.5, which is right here. It's above 2. That's ionic. Or you'll never go wrong with a metal and a non-metal. That makes it ionic. Very well. You need to remember one thing is that, and write this on the side here, the larger delta En is, the more polar the bond will be. So if I compare OH and ClH. Which one is more polar? Well, we did this already. We got a 1.4 difference. It was 3.5 minus a 2.1, and that's a 1.4. Cl is a 3. H is a 2.1. That's a 0.9. So this is a larger number, so this bond will be more polar. And this is going to be less polar. Be able to rank them, really. Okay, let's go back to a very important representation used for polar bonds. And those are partial charges, which you've seen above right here. We need to be able to use them. Quite simple. Let's begin with the partial positive. So again, looks like an S, but it's with a closed lobe here. You put the delta plus in a polar bond, so this is on polar bonds, on the less electronegative atom. Delta plus means more positive charge here because of less electrons, versus the delta minus goes on the more electronegative atom. Okay. So if I have OH, 3.5 for O, 2.1 for H, where does the delta plus, delta minus go? What do you think? So O is more electronegative, so that's going to be delta minus. H is less electronegative, that's going to be delta plus. Okay, finally, another representation is dipole moment. Dipole moment uses an arrow with a line crossing its tail. The line is pointing toward the more electronegative atom. It's pointing toward more electrons, and the tail is hovering above the less electronegative atom. And it doesn't matter what direction it is. It could be, as long as it can point again toward the left, as long as the bond is pointing toward the more electronegative atom. So here's HO. O is more electronegative. You can write it as OH, still points toward the O, because again, that's a 3.5 and that's a 2.1, 3.5, 2.1. Dipole moments are important. Partial charges are also important, so be able to apply both.